Hi students, welcome back to my next video, which is video 19 on an important topic in this chapter, electric field, Gauss Theorem. Students, we have reached the climax stage of this chapter. We learned electric field, electric flux, and the way you write electric flux due to a charge distribution over a closed surface in last two videos. You have to learn the concept that I discussed in last two videos, then the understanding of application of Gauss theorem will be very easy, right? You have three applications of syllabus, plus 2 physics, right? NCERT. Three applications. One, the electric field due to an infinitely charged straight wire, this uniformly charged wire, means linear charge distribution. Students, to find electric field, you use a relation E equals to 1 over 4 pi epsilon 0 Q divided by R square, which is derived for a point charge. That is a limitation. Coulomb's law applicable for only point charge. When you consider a charge distribution like the one, uniformly charged straight wire, to apply Coulomb's law is very laborious, very difficult. That's why Gauss theorem helps you to find electric field at any point near a charged wire, uniformly charged wire. Let us see how Gauss theorem is applied to find electric field to a straight wire. What is Gauss theorem first of all? That is phi 1 over epsilon 0 into Q. Electric flux through a Gaussian surface is 1 by epsilon 0 times the charge enclosed. You need to find electric flux through the Gaussian surface you consider. Equate that to this term 1 by epsilon 0 times the charge enclosed. You will reach an expression for the electric field. We will see. Very interesting. So I assume that you have learned the discussions of video 17 and 18. Now I will move on, right? Let us first of all consider uniformly charged wire. You can draw in your examination using a scale. You can easily write a diagram. I consider uniformly charged wire. This is a straight wire, infinitely long straight wire. Very simple, very easy to write down, right? So this is the wire, and here this extends up to infinity, infinitely long. You don't know where it starts and where does it end. You don't know. You don't know the end points. It's uniformly charged, means the charge per unit length is a constant throughout. Students, you defined in the video 14 charge density. How many types of charge density is defined? 3. Which are the linear charge density, surface charge density, volume. This is an example for linear charge distribution for which you define linear charge density. You will be using that now. Students, this is a uniform cross-sectional wire, and to find electric field just outside at a distance, certain distance. Now I will consider a point somewhere here or here, anywhere you can consider. If you consider a point here to find electric field, let me name that point P. You are interested in knowing, measuring the value of field at this point. How does it vary? What are the factors that affect the value of field? By the way, what is electric field there? If I write the field direction like this, you may wonder how to guess or understand the field direction this way. I will come to that point later. First of all, what is electric field? If you place a unit positive charge at that point, that experiences a force, that is F by Q naught, that is termed as field. You need not write always F by Q naught, just you write E, that's it. E means F by Q naught, force per unit charge. This is pointing outwards. Why? The charge distribution is positive. That's why due to repulsion it moves away. And the point is, if we extend the direction of the field, that direction or the line meets the conductor at an angle 90. Means what? the direction of field is normal. Normal to what? The conductor. How to decide that? I'll come to the point. First of all, you know or you think the field direction is normal to the conductor. To evaluate electric field here, using Gauss theorem, first of all, calculate flux. To calculate flux, you have to assume Gaussian surface. What is it? See, in my last video, one more question, I told you, Gaussian surface is an imaginary surface which encloses an amount of charge over which you evaluate electric flux. To solve problem easily, as I told you, we use symmetry property. Means we have to use symmetrical surfaces like a sphere, cylinder. What is symmetry? A cube, cuboid. What is symmetry? I have told you and I will explain you once again here. I am going to use symmetrical surface with respect to the conductor, that is cylinder. Now I am going to enclose some amount of charge by using a cylinder of length L, some L, small l. I will show you what is that length, and radius r. What is radius? Distance between the point where you are finding electric field and the conductor. What distance? Perpendicular distance. What is our perpendicular distance? Now using this distance r as radius, draw a cylinder. To draw a cylinder, students, I first of all write a straight line here. I can write a straight line. You do the same thing in your examination also. You do construction part like this only, right? Using scale, pencil. Now I have to measure this distance and I mark a point here. Here also I draw a straight line. Look here. It's very easy to draw using scale, pencil in your board examination, right? Clear? Now I have to write a circle here to show that it is a cylinder, right? What is the radius of the cylinder? R. Remember R. Here also I draw a circle. There are two end faces, circular faces, remember students, to a cylinder. This is a cylindrical Gaussian surface. Gaussian surface. What is the Gaussian surface? An imaginary surface which encloses an amount of charge over which you find electric flux, which is equal to 1 by epsilon 0 times the charge enclosed. What is the length of the cylinder? Length of the cylinder here is L. Remember, length of the cylinder is L, small l. Students, this conductor continues. That's why it's an infinitely long conductor. And electric field here is normal outwards. How it is normal outwards? What is the meaning of symmetry? Now I will explain that part using another diagram here. I am writing another diagram to explain you about the symmetry concept. Then I will rub this once you understand this. See, there is a uniformly long, infinitely long, uniformly charged wire, right? Now to find electric field at point P, same thing I am writing here to explain you. Point P, you have to consider a point at a distance r, right? Now you think of this as the charges are uniformly distributed around all along the conductor. I consider a small portion here. This charge repels unit charge at this point away, right? Students, now consider another very identical portion somewhere here at some distance, say L. At the same distance L down here, you can have another point, charge, right? Charge distribution, a small. If there is some dq charge, here to dq, here to dq charge. Students, this charge repels this unit positive charge. Which way? You draw a straight line and extend. This also repels the unit positive charge at the same time this way. Students, the same can be written for a portion here, anyway along this. For every point here down, there is a corresponding point at the same distance up here. You go higher up, here, there is a corresponding point down here from this. So every point below is a corresponding point for every point above. for which electric fields can be shown this way. Now, if you resolve the value of this, you can find, see, you draw parallelogram, right? Parallelogram. You know how to find the resultant, resolve to a vector into two components. If this is angle theta, this part becomes what? E cos theta. And this part becomes what? E sin theta. E sin theta, where E is the value. So this is also at the same distance, that's why value E only. If you draw parallelogram, this part becomes E cos theta and this part becomes E sin theta. Students, the vertical components, namely E cos theta downwards of this and E sin theta downwards of this and E sin theta upwards of this. Component, upward component of E, which is E sin theta, downward component of E, which is E sin theta, being equal opposite, cancel each other. Therefore, the horizontal components, namely E cos theta add with E. The same thing can be explained for a point charge here. Therefore, this is what we call symmetry. Therefore, the electric field due to the entire conductor will be along the normal to the conductor. Is only along the normal to the conductor. Let it be E. This is what you have to remember. You need not explain this here. Understood, students? So this is called symmetry. For a very point up here in the conductor, there is a corresponding point down here. So field due to a point down is equal to field due to a point up here. And if you resolve them, you will get horizontal fields which add with E. Whereas vertical components cancel each other. Therefore, unit positive charge tends to move along the radially outward direction. Which direction? Radially outward direction. That's why field is along the perpendicular to the conductor. Here also it is along the perpendicular, normal, radially outward direction. If the charge is negative, you will write direction like this. Here it is positive charge distribution. That's why you write electric field like this. This is very, very important observation, students. All these things you need not write in the exam. Only write the diagram, write the expression for flux. I will show you. Then you will use Gauss theorem, simplify, you will reach the expression. That's it. But you need to know all these things. Very, very important. Now I will rub this. Now you understood, students, why field is radially outwards. Very, very simple. Now, to find electric flux through the entire Gaussian surface, what you have to do? Imagine a small area of cross section around the point P, whose area some ds, differential area, very small, infinitely small, over which electric field is supposed to be uniform. All the points electric field is uniform radially outwards. And one more point you need to know, to this surface area, the unit vector is how? Perpendicular. That is also along the same direction. That's interesting, right, students? That's why symmetry has a role to play. Symmetry advantage is this. The electric field and normal are along the same direction. So what is theta? Theta, angle between these two, equals to 0 degree. What is cos 0? 1. We will use it. Means you are going to divide this curved part into smaller areas, ds. You will find flux over each surface area ds. Then you will add them to find total flux, right? Therefore, total flux is electric field value into total surface area. Why? Due to infinite long conductor, the field is radially outwards and same, uniform all around the surface, outwards. That's why, since electric field here E, here E, here E, here E, here, everywhere around the surface E. That's why you can just write electric field into area. Electric field into area. You will write an expression for flux. And what about these two surfaces? I'll shade these two end surfaces. Look here, friends. These end surfaces or just parallel to the electric field. See how the electric field here is just along this direction, right? And what is the normal to this? The normal here is up to the surface. To the surface normal is up. But for this surface normal is right. Field is right. Here what is the angle between the two? 90. What is cos 90? Cos 90 equals to 0. Therefore there is no flux through this. The same is the story with the bottom surface. Here also electric field perpendicular to the normal to the area. Again, the angle between electric field and normal is 90. What is cos 90? Cos 90 is 0. So there is no flux through the horizontal end faces. Horizontal end faces. Only along the curved surface. Only through the curved surface. Only through the curved surface. But along radially outward direction. Radially outward. Outward like that. Friends, this much you have to remember. In our discussion, here you remember, you explain the diagram. I have given explanation in your notes, short notes given. There you explain like this. Consider a uniformly long straight wire charged with a uniform charge density lambda. Here what is lambda? Lambda is uniform charge density. Uniform charge density. Right? Uniform charge density. How do you define charge density? Lambda equals to dq by dl. For a small elemental length dl, charge is dq. If you want charge, you can write dl. If you want charge, you can. Therefore, what is charge on a given length? Lambda into dl. Going to use this. Remember. And what is L? L is length of the Gaussian surface. Length of the Gaussian surface. Length of the Gaussian surface. Friends. Next, one more point. R. What is R? R is perpendicular distance. Which distance? Perpendicular distance of the point from the conductor, straight conductor, perpendicular distance of the point from the conductor. These explanations you write in your own words, right? Next, to find electric flux expression, you think of this situation. I have explained in your notes, you write like that. There is no contribution for flux through the end faces, as electric field is along the end face, normal is perpendicular, angle is 90. What is cos 90? 0. Same is the story here. The electric field is along the end face and flux is normal, right? Therefore, the electric field, look here, this is duster. Electric field is along this and normal is like this. What is the angle between them? 90. Cos 90? 0. However, the field is perpendicular to the curved surface. And at each point, the field is normally outwards to the conductor and uniform. Everywhere field value is same. That's what you have to remember. Therefore, you need to find flux through the curved part of the surface. Curved part, right? So, let us write the expression. What is electric flux? Electric flux, I write here. Electric flux through the curved surface of the cylinder. Curved surface of the cylinder. What is that? Is flux equals to field value at each point, field value at each point into surface area of curved part of the cylinder. This you know, right? Surface area of curved part of the cylinder. Therefore, what is flux phi? I write here. Flux phi in this color piece of chart. Phi equals to, what is electric field at each point? E into what is surface area of a cylinder. You know, high school you have learned. What is that? 2 pi r. 2 pi r. Circumference into length. L. 2 pi r L is the surface area of cylinder. Surface area times electric field. Electric field at each point into surface area, because electric field is same all around. This is symmetry. Every point to the right on the cylinder corresponds to a point on the left surface of the cylinder, or at the same distance. So electric field value remains the same. That is symmetry. See, if I stand like this, symmetry. My hands, symmetry with respect to the body. This side, this side. Now asymmetric, now asymmetric, now symmetric, now symmetric, now asymmetric, like that. So distance of this point, this point, this point, this point from the conductor same as the distance here. That's why electric field value same. It's flux expression. Right, students? Now you have to use Gauss theorem. What is Gauss theorem? I write here. Gauss theorem. Gauss theorem. What is Gauss theorem? We know electric flux phi equals to 1 by epsilon 0 times the charge enclosed. 1 by epsilon 0 times the charge enclosed. Students, how do you find charge? Since you know charge density of the conductor, right? What is charge Q? Charge density into length. I have considered how much length? L. Per unit length charge density lambda. That's why you call this equation 1 and you call this equation 2. And now the charge on the wire, charge on the wire of length, charge on the wire of length L is Q, that is Q equals to what is charge? Charge density into length. What is charge dq? Charge density into length. Charge dq for dl, q for l, q for l, length l. You call this equation 3. Use 3 and 2, 3 and 1 into. What is 2? Phi. What is phi expression? E 2 pi RL. E 2 pi RL. I write here. E 2 pi RL equals to, what is the value on the right side of 2? 1 by epsilon 0 times the charge lambda L. Students, lambda cancels. You solve for E. What is E? 1 over, you cross multiply 2 pi R here, you multiply 2 pi with epsilon 0, a constant, into R is there in the denominator, numerator lambda. What is lambda? Charge density. Which charge density? Surface charge density. Now we can write vectorially, the expression is E equals to 1 by 2 pi epsilon 0 times the lambda by R, right? Unit vector direction. See, direction of unit vector. Unit vector is radially outwards, right? Unit vector is this vector notation. If you write vector form of the expression, what is the meaning of this? Students, electric field due to a linear charge distribution, infinitely long, no ends, infinitely long. Electric field is completely radially outwards. Whose value depends on two things. One is charge density proportional to charge. Which charge density? Linear charge density. Inversely proportional to perpendicular distance. As perpendicular distance increases, the field value decreases. So this is inverse relation. You can write graphical variation. Take electric field along the y-axis and along x-axis, or as R increases, E value decreases. So it is a rectangular hyperbola like this. See, as R increases, field value decreases. This type of variation, you arrive at this relation, this fetches you 5 marks. Very easy. The application of Gauss theorem. Gauss theorem is phi equals to 1 by epsilon 0 into charge. What is phi? Electric flux. What is flux? Electric field at each point into curved part of the surface area of the cylinder. Why you don't consider end faces? Because the field is parallel to the end face, perpendicular to normal angle theta 0. It is not flowing through. Field is not flowing through like this. It is not flowing. It is just along. So flux through this 0, through these two ends. That's why, what is flux? Field value at each point into surface area of the curved part, which is 2 pi r L into E. And for charge, which relation? Charge is charge density into length. Use this relation and 1, 3 and 1 into, for phi 2 pi r L into E. Right side charge lambda L 1 by epsilon 0. Lambda L cancels. So E is magnitude form 1 over 2 pi epsilon lambda by r, and vector form this. The field is radially outwards for positive charge, radially inwards for negative charge. Okay, students, we will run through the first application. Gauss theorem, first application, electric field due to an infinitely long, straight, uniformly charged wire as in your study material. How much you have to write in the examination. First of all, you write this diagram. Look here, this is a uniformly charged, infinitely long wire, straight wire, is a linear charge distribution, and this is Gaussian surface, cylindrical surface. Electric field here is normal, that is radially outwards, right? For this diagram, this is the explanation. This is what we have in our study material. Lambda uniform linear charge density, R perpendicular distance from the point P from the wire, L length of the Gaussian surface. Then the Gaussian surface is cylinder having length L, radius R, wire as the axis. The electric field at all points, this is very important point, students. Electric field at all points of the Gaussian surface is same. Why same? Distance same. That is symmetry. Same, and is normal to the curved surface of the cylinder. Okay. Electric field is normal to the curved surface and has same value all around because distance is same. That is symmetry. Next, the flux through the Gaussian surface, electric field at one point into curved surface area of the cylinder. That is E into, what is surface area of a cylinder? 2 pi RL, that you know formula, right? We'll go to the next page, students. By Gauss law, what is flux? Flux is 1 over, I wrote this. Flux is 1 over 4 pi epsilon, 1 over epsilon 0 into charge enclosed. This is equation 2. This is Gauss law. By definition of linear charge density, what is that? Charge per unit length. So what is charge? Lambda into L. This is equation 3. Now using equation 3 and 1 into, what are we doing? Using equation 3 and 1, right? 1 we write in the first page and 2 here. Using in equation 2, what is 2? Gauss law. Now if you write left side phi E 2 pi RL, right side Q lambda L, you simplify, L cancels, the rest is, you can write one term extra here, note down in the textbook as your notes, you continue, E into 2 pi R is equal to 1 by epsilon 0 into lambda, or you can write E equals to 1 by 2 pi epsilon 0 is a constant, lambda divided by R. This is magnitude form, dear students. You write this, you complete this part, then come to the vectorial representation, that is vector E is equal to lambda by 2 pi epsilon 0 into R. This is another expression. It's vectorially you write E vector equals to lambda by 2 pi epsilon 0 into R, unit vector. What is unit vector? Direction of electric field. If the charge is positive, it is pointing outwards perpendicular to the wire. If the charge is negative, pointing inwards perpendicular to the wire. This is the expression. You write this part also, you know, you can simplify. Totally I have written vector notation, that is E vector equals to lambda by 2 pi epsilon into R n cap. If you are solving problems using this, you don't bother about the direction, just use lambda by 2 pi epsilon 0 into R. That part you have written here. You complete this in your notes also. You continue here. 2 pi R into E, L cancels, equals to 1 by epsilon naught into lambda, and this is the formula. Magnitude form, vector form. That's the students. If you write this much, it fetches you 5 marks. Very important. Practice this thoroughly. Then we will move on to next application, that is field due to a uniformly charged infinite plane sheet. We will come to that in the next video. Thank you.